Hey guys, okay. So I'm gonna try and make a video for you guys. I try to do this over winter spring break, but then we got a message from Ms. Clapsaddle saying that parents are writing in saying that we shouldn't be giving you guys work. And I mean, I get it. I understand. I mean, this is an AP class, but you know, I decided just to go ahead and give you guys the time. That being said, though, we still have a lot of content to go through. So what I'm going to do is on the days that we're not meeting, I'm going to have you guys work on something like this, which is going to be like a video lecture. All right, I'm going to try and keep them short, but you are going to have one on the days that we're not meeting. So anywhere from 2 to 3 of these per week. Okay. You're going to have to spend your own time, either that or we add another class to the AP section. Okay. So we're going to try this and see if it works. We're going to do a little bit of review, okay? We're going to take the element rhodium, which is element number 45 on the periodic table, and we're going to review quantum numbers and electron configuration, okay? So as I go through the electron configuration, I'm going to go ahead and start adding electrons. Remember that as we go across a period on the periodic table, every increase in number of protons results in an increase in the number of electrons. And as we increase the number of protons and electrons, we're actually changing the element. So if I want to get to element 45, that means I have to have 45 protons and 45 electrons. That means that my electron configuration here should also have 45 electrons. Now, as I go through the second period, I'm going to show you what each electron represents. So for example, 2s1, 2s2, 2p1, 2p2, 2p3, 4, 5, 6. So in the second energy level or the second period, okay, we've placed 8 electrons, 2 in the s orbital and 6 in the p orbital. In the next row, I'm going to do the same thing, except now I'm going to show you exactly which element each one of these electrons represents. So if you're looking at your periodic table, or if you want to pause the video and pull one out, we can work through this together. All right, so I'll give you a second. Pause the video, get out your periodic table. Okay, now if you have your periodic table out, if you go to the third period, which starts with element number 11, that is element Na, which is sodium. Sodium is represented with this electron. Next to sodium, we have magnesium, which is represented with this electron. Jumping across to the other side of the 3p, we have aluminum, all right, silicon, okay, phosphorus, sulfur, chlorine, and then the noble gas argon. So each of these little arrows represents an electron, which in turn represents an element. So as you go through the electron configuration, all you're really doing is putting the elements into their respective orbitals, okay? So now we're in the 4s. So the 4s1, 4s2. From there, remember, we go to the 3d. So we got to go through the entire D block. That's going to take 10 steps. Remember, treat electron configuration like a roadmap. So I'm going to add 10 electrons. Okay. Then from the 3D, we go to the 4P. This one starts with element number 31. This is gallium, germanium, arsenic, selenium, bromine, and krypton, right? Okay. Now we go on to the 5s, okay? So 5s, we have 5s1, 5s2. From there, we go to the 4D, okay? So starting at element number 39, this represents yttrium, okay? Now, I want you guys to notice, remember that when you're adding electrons to your electron configuration, you have to go through and add all the positive spin electrons, all the up arrows first, until the entire block is full. Once you have all the empty spaces or the subshells in this block, then you can go back and you can double up, okay? So yttrium, zirconium, which is Zr, right? Niobium. Then we go to molybdenum, technetium. Now that all my subshells are full, Now I can go back and double up, but now my electrons are going to have a negative spin. So from technetium, I go to ruthenium. And then from ruthenium, I go to element number 45, which is rhodium. So this electron right here, right? This is the electron that represents RH. It's the 45th electron in the configuration, and that's the one that represents RH, rhodium, okay? All right, now let's do our electron configuration shorthand. Again, this is review. All right, we're gonna do the orbital notation. So I'm gonna just write the name of the orbital, 1s, and then 2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d, 1, 2, 3, 4, 5, 6, 7, 4d7. Okay, that's going to be our element. Double check, 1, 2, 3, 4, 5, 6, 7. Yes, so that's going to be the orbital notation for rhodium. Okay, if I wanted to do the electron, the noble gas notation, well, I go up one row, right, which is the 4th period. Then I go all the way to the end and I get to krypton. So krypton is basically going to replace this configuration right here. Because all of this, if you were to follow this configuration to its end, you would end up at krypton. So I'm going to replace all that with my noble gas, krypton. Then I just have to put the configuration of whatever row we're in to get to our desired element. So this is our orbital notation, and this represents our noble gas configuration. Okay, that's all review. Now, what we're going to discuss right now is going to be the quantum numbers. So what are the quantum numbers that represent rhodium? Okay, now remember, every element has a unique set of quantum numbers. There's not going to be two elements that have the same set of quantum numbers. So each one is going to be individual, kind of like a footprint. All right, so let's go through real quick and let's figure out what quantum numbers are represented for rhodium. Okay, I'm going to scroll up a little bit. The first one we're going to talk about is the primary quantum number. The primary quantum number is the number that is represented by the energy level of the electron. Energy level of the element / electron in question. Okay, please take a minute to write these down. Okay, now the energy level is represented by the period of the periodic table. So for example, if you look at this guy right here, the energy level is 1. So the primary quantum number for any electrons here would be 1. Here, let me scoot this over just a little bit. These guys here are in the 2nd period. So the energy level here, or the primary quantum number here, would be 2, right? Now, what's cool about doing the electron configuration is all you have to do is take a look at the energy level that the energy level of the electron, right, or the subshell of where the electron resides. So for example, this guy right here is our electron, right there. That's the electron that we're looking for. That's rhodium. If you look at this guy right here, you can see that rhodium is in the 4D. So because rhodium is in the 4th energy level, right, then the primary quantum number for rhodium, and this is represented by N, is equal to 4, because rhodium is in the 4th energy level. i.e. the 4D, right? The 4D gives you a primary quantum number of 4, okay? So that's our first quantum number. The second quantum number that we're going to work with is called the azimuthal quantum number, okay? The azimuthal quantum number represents the orbitals. So this one represents the orbitals, right, of an atom, right? The orbitals of an atom. So when you're looking at the azimuthal quantum number, right, you have 4 possible values for that. Here are the 4 values that you can have. It is 0, 1, 2, 3. These are the 4 values of your azimuthal quantum number, right? And basically, when you select the numbers, the highest value you can go when you're selecting these, right, is to n minus 1, right, to n minus 1. And I'll show you what that means in just a second. So when we're dealing with the azimuthal quantum number, okay, the highest value is n minus 1. So that means that for this one, if my primary quantum number is equal to 4, right, then the azimuthal quantum number is equal to n minus 1, which is 4 minus 1, which is 3. So here's what this means. What this means is that it can be any one of the options up to number 3. So it can either be, right, 0, 1, 2, or 3. Well, the highest value it can go is 3. So in this case, it's 0, 1, and 2. It can be any one of these values. Now, each one of these values represents an orbital, okay? 0 represents s orbital. 1 represents p orbital. 2 represents d orbital. And 3 represents the f orbital, right? Each one of these numbers corresponds directly to an orbital. Now, in the case of the azimuthal quantum number for this particular element, it's going to be in one of these 3 orbitals, okay? It's going to be either in the 0, which is the s, it's going to be in the 1, which is the p, or it's going to be in the 2, which is the d, okay? In this case, we know that it is in the 4D, right? So because the electron exists in the 4D orbital, then the value for our azimuthal quantum number has to be this guy right here. It's going to be in the d orbital. So for L, in this particular instance, right, I'm going to scoot over a little bit. L is equal to 2. L is equal to 2. I'm going to put these to one side so we can make sure that we keep them together. This one is going to be n equals 4. Okay. So once again, the azimuthal quantum number represents the orbital. There's only 4 orbitals, the s, the p, the d, or the f. So your electron is going to lie in one of those 4 orbitals. Whichever orbital it is, in this case, it's the d orbital, you're going to pick the corresponding value of L for that orbital, okay? All right. Next number is the magnetic quantum number. The magnetic quantum number is the number that ties in with the azimuthal quantum number. So M sub L is all values of negative L to positive L, right? Negative L to positive L. So when you're looking at the magnetic quantum number, you figure out, okay, what is your L? So in this case, L equals 2. Therefore, my values for my magnetic quantum number are going to be all the values from negative L using whole integers to positive L. So that's going to be negative 2, negative 1, 0, 1, 2. Now, what does a magnetic number represent? The magnetic quantum number represents the subshell. The subshell in the orbital. Okay. Now, I want you to look at something. I want you to look at the M sub L values. You have negative 2, negative 1, 0, 1, 2. And if you look, this is 1 subshell, 2 subshells, 3 subshells, 4 subshells, 5 subshells. If you look at the d orbital, let's go up to the 4d, you have 1 subshell, you have 2 subshells, 3, 4, 5. Hey, what's going on here? If I have 5 subshells, right, then those M sub L's numbers must represent each subshell. And that's exactly what they represent. Look, this is your negative 2 subshell. This is your negative 1 subshell. This is your 0 subshell, your positive 1, and your positive 2. So when looking to assign the magnetic quantum number for your particular element, you have to look at the subshells that are in the orbital. But the 4D orbital contains 5 subshells. Once you've done the electron configuration, you should be able to identify which of the 5 subshell houses the electron that represents the element. So when you're looking at rhodium, this is the electron that represents rhodium. And if you look at the subshells, this electron resides in subshell -1. So the magnetic quantum number, right, for rhodium is going to be M sub L equals the -1 subshell, the -1 subshell. Okay, that's how those work. The last quantum number is the spin quantum number. So in every subshell, right, in every subshell, let me go ahead and get a different color here. You have two possibilities, excuse me. Okay, you can have a subshell that has 1 electron. If it has 1 electron, that means that that subshell contains a positive 1/2 spin, right? Or you can have a subshell that has a positive and a negative electron. Like for example, this guy has both. So if your element resides, right, if it's this electron, for example, if it resides in a subshell that has both a positive and a negative spin electron, then your M sub S is going to be positive -1/2, right? So M sub S for this particular element is this guy here. You can see that we have a positive spin electron and a negative spin electron, and rhodium is the negative spin electron. In that case, my M sub S for rhodium would be positive -1/2. Now, depending on who you ask, right? It can either be one of two things. It can either be a positive -1/2, or it could mean that yours is the -1/2 spin electron. Different books explain it different ways, but they're both technically right. If you're looking at the spin in the subshell for that particular electron right here, you have both a positive and a negative spin electron, right? So this is the spin of that subshell. It's both positive and -1/2. If you're looking to identify the specific electron, for example, the rhodium electron is this one right here, the one that I've circled, right? The rhodium electron has a negative spin. So you could also say it's just a -1/2. I will accept both, but I do want to make you guys understand that different places will refer to these in different ways. So please understand both, okay? This represents the entire subshell, the subshell, and this represents the individual electron. All right, they're both technically right. As far as the 1/2, it's always either going to be positive or negative 1/2. That's all you have to know for that particular quantum number. So if I'm looking at the element rhodium, for example, right? Rhodium. Okay. Then here will be my quantum numbers. N equals 4. L equals 2. M sub L equals -1. And my magnetic spin is equal to positive negative 1/2 or just a negative 1/2, right? Okay, those are the quantum numbers. Now, there's not going to be another another element that's going to have this set of quantum numbers, okay? Quantum numbers are like the footprint. If the electron configuration is the address, then the quantum numbers are the fingerprint or the footprint, okay? Everybody's going to have their own set. So in short, right, when you're looking at an element, the quantum numbers will give you precisely the identity of the element that you're looking for using these series of numbers. What I want you guys to do for me in the Google Classroom, okay, is I want you to give me the quantum numbers for this element. That is number 52. Okay, I want you to provide the quantum numbers for this element. If you guys have any questions, please feel free to rewatch, send me an email. I'm going to assign this today.